Welcome back to the third session or the third lecture on Anova. So now we look at the model assumptions. The assumptions that we had to check were three, and we'll go through those again in a second. First of all, the model equation. We're assuming that the observations are essentially just some mean, mu I, and some random variation around the mean. So this is what the data looks like here essentially. Now, EYIJ and mu I, because this belongs to group I, so the mean is mu I. And the expected value of the residuals should be simply from the model equation. Residuals are the observation minus the mean. So residuals observations minus the mean. But this is 0 because this is the mean for that. Because we know that E of Y minus its mean will be 0. So that disappears. That means the other terms have 0 mean. What about the variance? Variance of epsilon ij is variance of y ij minus mu I. This is a constant, so this doesn't affect the variance. And so this is just the variance of the y ij, which is sigma squared. I'm assuming all the variances are the same. Now the fitted value is essentially the group mean. For y ij, the fitted value y I hat is the group mean. This is the estimate of mu I. And the residuals are defined as observed minus fitted. So it's yij minus yij hat. Or if you like, that becomes essentially yij minus yi bar. So residuals are automatically calculated in R, and you can use them for purposes as we'll see. So the assumptions here we can write in terms of residuals. The residuals or the error terms are normal. They have a constant variance. That means the variance doesn't depend on the group they come from, and they are independent. Or I can write the thing in one hit as EIJ are IID independent and identically distributed, normal with mean 0 and variance sigma squared. So these are the three assumptions I have to check. So normality of error. There are two ways of doing this essentially. In fact, there are also tests for normality, but we will not cover the test. The first is plot a histogram of the residuals. If they look normal like their first one, then there's no reason to doubt normality. But they can be skewed to the right, to the left, or kind of a cliff of this kind, for example. In these cases, the last three cases here, so this is okay, but here we will doubt if these residuals come from some normal process. The other way is what's called the normal QQ plot. And so here, what we should see is that the points are along a straight line, and the straight line has been drawn to guide you here. So you can see the data that's right skewed, and the line disappears essentially, but this actual, and there's a bit of a cliff here as well. There's a problem here in both ends. So you're going to get something that gives you a strong departure from the straightness. So the last three cases here don't look normal at all. Constant variance, we'll plot the residuals against the group means, the residuals against the groups essentially. And what we expect to see is, for equal variance, the data or the residuals should lie within a band of that kind. There's some outliers over here, but nothing serious. What we're looking for as far as unequal variance is concerned is typically we have what's called fanning outwards or fanning inwards. And of course you can have something that looks like this. There's nothing, data may look like this. It may be all for that group, and then a small one there, and then a big one there as well. That's also possible, but fanning in and fanning outwards indicates some systematic change in the spread with the group number. So that's just constant variance terms. There are also tests for constant variance, as we saw earlier in the two sample case. There's something called the Bartletts Test. The assumption is H0 is all the variances are equal, and H1 says they aren't all equal, and so we can use Bartletts Test, and the p-value will dictate to us whether we reject H0 or don't reject H0. And alternatively, as for the two sample case, if you look at the largest and the smallest variances and look at the ratios, you'll find if the ratio is 1.5 or less, you can easily accept that the variances are equal. Independence is hard to check. We won't cover that in this course. So here's an example, the milk data. First of all, histogram of residuals and the residuals against fitted values. Histogram doesn't look great, but certainly there's no huge problem. It's reasonably symmetric, and I can change the shape, of course, by having more or fewer bins. If you look at the fitted values against the residuals here, again you will find that there is not a huge problem as far as here the means, as you can see, and the residuals that way. There's not a big change in spread over here. So based on those two, normality, histogram looks fairly symmetrical, no problems there. Equal variance. If I look at the maximum and minimum, I find there's a problem here. 2.43 it says, which is bigger than 1.5. But if I actually use Bartletts tests, I get a p-value of 0.6736. So the test here is more accurate, especially because I've got very small sample sizes here. For so small sample sizes, it's very hard to judge whether things have equal variance or not just by looking at the spread. And so the test is more accurate. So in this case, I can find the p-value is quite large, and there is no reason to doubt the equal variance assumption in this case. So that's how you test for the assumptions of the Anova. We'll go over the rest in the next lecture. Thank you.